All right, so last time we briefly talked about word embeddings. So the naive approach is to use one-hot encoding. So say you have a dictionary that turns a string into a number, and the naive approach to interface this number to our LLM is to turn this into a vector where it's all zeros and has one in the corresponding location of the dictionary output. So for example, if you have size 100,000 dictionary, so you have 100,000 tokens in the dictionary, then this one-hot encoding representation will be of dimension 100,000, which is in fact too large. So a better approach is to use word embedding. So if you have a large dictionary, you can use a continuous representation, but use smaller dimensions. So I guess the most naive approach is to use a randomly initialized lookup table, upsize number of vocabularies, and some embedding dimension, which is low dimensional. So this will be a typical output. So say you have a dictionary that maps the input string to a series of numbers, and you will be basically looking up different rows of this random matrix. Of course, this will not capture any meaning of the underlying token and their relations. So in fact, as opposed to leaving these matrix as is, you can train them on some tasks. And one of the pre-trained embedding, which is famous, is called glove embedding. And this is included in the directory. So we'll be loading this and making some visualizations. So what's a word embedding? For each word in the dictionary, it's going to have some n-dimensional continuous vector. But in this vector representation, it's going to capture some meaning amongst different data points. Sorry, amongst different tokens. Okay, so let's go ahead and load the glove embedding. Okay, so it has 400,000 tokens, and each token is represented as a 50-dimensional continuous vector. Okay, so let's load it in our matrix, and let's call this lookup table. So in PyTorch, we're going to create an empty tensor and load this matrix into PyTorch tensor. PyTorch tensor is an ND array or a tensor where given this tensor, you can do lots of operations with it. Element-wise, product, matrix multiply, everything. Okay, so here we're going to create a word embedding class to help us do some processing. Okay, so let's try to embed this word here, hello. And the corresponding tensor representation is following. And now we're going to do some visualizations. So it has interesting relationships. So we're going to first project the embeddings into two-dimensional space so we can visualize these embeddings. And we'll be using dimensionality reduction technique from scikit-learn library. So it has interesting relationships. So for example, if you embed the word king into glove embedding vector and subtract the embedding for men and add glove embedding for woman, it will be very close to the word embedding of queen. So you start from king, subtract this vector man, add in vector woman, then it's going to be very close to the embedding for queen and etc. And same thing for verb tense, start from walking, subtract swimming, add swim, then it's going to be projected to a space where it's very close to walked. Same thing for country capital. Say, for example, you start from Spain, subtract Russia, add Moscow. It's going to be very close to Madrid. So well pre-trained word embeddings capture these relationships amongst different tokens. So let's see if that's true. So there are many different ways to down project a high dimensional vector. And here we're going to use our random projection. So what it does is it creates a random matrix, IID matrix, and just does a matrix multiply with this random matrix. So this matrix is going to be of size d by 2, so we can down project high dimensional vector to 2 dimensions. Okay. So these are some helpful functions to down project them to 2-dimensional embedding vector, and some helpers to draw points and arrows. Okay, so let's first do this gender transform. Okay, so what have we done? So we have embedded king, queen, man, woman, and we've visualized the difference between 2 vectors. I think it more or less looks pretty similar, but not exactly the same. How about countries and capitals? Okay, so different vectors. I think this is okay. So each vectors start from country to capital, and these difference vectors are not the same, but some of them are almost the same. It looks like London, UK, Beijing, China, it's almost the same, and so is Moscow, Russia. Okay, so let's do some arithmetic in the 2D space. So let's start from Russia, add in London, subtract UK, and see if it's close to Moscow. Okay, so we have projected various capitals, and we started from country Russia, added in London, subtracted UK, and we're drawing some nearest neighbors from the space. And looks like Moscow is the nearest neighbor among other capitals. Okay. So how about cosine similarity in the embedding space? Okay, so we've done the same arithmetic. We started from king, added, subtracted, what was the arithmetic? We added woman and subtracted men, I think. And we're going to be looking at cosine similarity of 2 vectors. One after arithmetic, and y is other candidates. So it seems like among the candidates, queen has highest similarity, daughter is second similar, prince, throne, princess etc. Yeah, so we start from king, subtracted man, added woman. We're looking at cosine similarity between the output, V, against other candidates. So I think we're looking at how many? Yeah, top 5 ranking nearest neighbors in the embedding space. So I think it makes sense. Start from king, and I don't know how daughter is the second similar object, but these are all, I guess, related in some sense in natural language. Okay, so this is the end of lecture 5, and in today's lecture, we are going to do an MLP network building. Okay, so go ahead and open up lecture 6. So the goal here is to introduce multi-layer perceptron and various activation functions and stacking multiple layers to build an MLP. And from here and there, we're going to be using PyTorch. And I suggest you do a self-study. But like I said in lecture 1, try not to overstudy. Just for these types of stuff, just study just enough so you can follow through. It's a waste of time for you to go and try to learn every API in PyTorch. Okay. All right, so first thing, a linear map. So from now on, we're going to be dealing with ND tensors, not just 2D matrix. So an ND tensor, or linear map, is going to be a real matrix of size D1, D2, all the way to dk times n in. And that's going to be the input. And this matrix that commutes with a data x is going to have size n in by n out, but not necessarily. This can be more complicated. And output is going to be some ND tensor where the innermost dimension is commuted. Okay, so as you can probably guess, these are going to correspond to various things like batch dimension or things like this. So very soon we're going to start using GPUs, and in GPUs the whole point is to do parallel processing. So as opposed to processing one data at a time, like we're doing right now, when we use GPUs, we're going to process multiple data at the same time. So the outermost dimension is most likely going to be the batch dimension, and the second dimension is going to be, I guess, n in or something like this. And for images, it's going to be batch times input channel, output channel, things like this. Okay, so linear map is a linear function where you have input data and you have this matrix plus and bias. And this is, linear class, the constructor, we have weights and biases. Weights are going to be random initialization drawn IID from standard normal distribution, and bias we're simply going to set it to 0 for now. And here now let's implement the forward component. And when you implement this, we're going to test the implementation with a batch size of 2 an input dimension of 64, output dimension of 256, and the input X is going to be some random matrix, and we're going to instantiate this linear class and call this function, call this instance object on X, and check the size of X and Y makes sense. So what is the expected size of X and Y? Expected size of X is what? Here it's given already, batch size by input dimension. What is the expected dimension of Y? And so input shape is size, batch size by input dimension, so 2 by 64, right? And output dimension is of size, right, 2 by 256. Batch size times output dimension. Okay, so let's implement this quickly. So I guess you've done a similar thing. Need more time? Oh, by the way, I think the Lecture 5 solution IPython notebook is available on ETL. Yeah. So you might want to look at this PyTorch documentation if you have never used it before. You don't need to know everything, so just basic I think should be enough. Here's how you create a tensor of size ND tensor, and you can also even import from NumPy object, and you can create a tensor pre-filled with ones or some other data, and this is how you create a random tensor, PyTorch tensor, all ones, all zeros. Has many attributes like shape, data type, and device. This is whether the PyTorch tensor resides on GPU memory or CPU memory, etc. And this is how you index torch tensors. And you can concatenate 2 tensors or 3 tensors however you like. And you can do various arithmetic. So here, if you want to multiply 2 tensors, you simply call torch.matmul for matrix multiply. And or if you have, if you already have a tensor, you can, let's just say this guy's name is tensor A. Just say tensor A.mul tensor B. This is another way to do this. And what else? You can do in-place addition. Yeah, if you have a NumPy array, you can import it into a PyTorch tensor and things like this. Yeah, pretty basic stuff. So I think this is going to take you like 5-10 minutes to look at it at most. And other things, if you encounter something that you don't understand, just look it up and try not to overstudy. I guess in a given amount of time, I would rather spend time understanding the underlying principles rather than some PyTorch or NumPy details. Okay, so let's look at the solution. We already looked at the solution in the tutorials file, I guess. There's two ways to do it. You can do torch.metmol or tensor8 dot, was it mol? Yeah, mol dot torch8 dot mol, another tensor. Okay, so input x and the weight, and that's the output, and you add in the bias. That's going to be the for definition of linear class. Okay, and let's see the dimensions check. Right, so input dimension is as expected, batch size by 64, and output size is batch size by 256. So let's check the input and output distributions. So we created some random tensor as input, created another random tensor for the weight, and I think the bias is initialized to all 0. So let's look at the input and output distributions. So Matplotlib has this nice function called hist. It gives you a histogram of how many bins you like. And let's see. All right, so this is the input distribution versus output distribution. So this distribution on X, this distribution on Y. So what's the problem? So suppose we're going to stack various linear layers on top of each other. And what do you think is going to happen? Right, right. So as we keep multiplying these matrices over and over, then it's going to blow up to a very large number. And depending on which nonlinearity we use, say we use something like 10H, where it has 0 gradient when input and output, when input to the nonlinearity is very big, then it's going to have 0 gradient and it's going to be stuck. Okay, so we looked at the histogram. Yeah, so it's going to lead to numerical instability when we stack multiple layers for the MLP. So we have already looked at this during the class lectures, but just to review one more time, let's assume the elements in W are mutually independent and they share the same distribution. In the beginning, this assumption holds, right? So they're initialized from IID standard normal distribution. And this analysis is going to hold for beginning of the training phase, not entirely throughout. So, so at least in the beginning of the training, same assumption holds for X, and assume W and X are mutually independent. So if we look at the variance of the output in the, say for example, kjth dimension, so this is going to be the variance of a slice of the weight matrix inner product with the input data plus some bias. And with the IID assumptions, this is going to be n times the variance of xki, wij, and if these two random variables are independent, it breaks into three terms, but we assumed zero mean, so these are going to go to zero, so it's going to be the variance of the product of the two random variables. And in order for the variance of x to remain the same with variance of y, throughout iteratively applying these linear maps, we would like the variance of the weight to be 1 over the number of input dimensions. And this is the forward view. And backward view, we had variance set equal to 1 over n out, the output dimensions. And the idea with Xavier was to use a harmonic mean between 1 over n in and 1 over n out. So here, let's keep it simple and just stick to the forward view. Okay, so now let's try to fix this. So let's come back to this linear class. And input and output is the same. The weight is initialized with IID standard normal distribution. And we want to rescale this weight matrix so that the variance of input and output activation remains the same before and after applying the linear map. And again, the bias is initialized to 0. So let's apply some fix here. And you don't have to worry about the forward call. We have already given it. So let's just try to fix the initialization. And then do the same, where for the same sized tensors, we're going to draw the histogram. And once you see the histogram, try to compare it with before adjustment and after adjustment. So this is before. And let's see how this changes once we apply the fix. Okay, as expected, as I'm walking by, somebody's giving me a beautiful histogram, and some people are opening up Core Lab, and some people are texting. Okay, so the fix is quite simple, right? So here, you just do element-wise division by a constant number. So you want to divide by the square root of the input dimension here. Okay, so let's see. Okay, looks very good to me. Just look at the scale of the x-axis from -2 to 2. Here before it was -20 to 20. So we have a factor of 10 decrease in the support. Okay, so next thing. Now let's look at various activation functions. So in the lecture, we saw all these guys and even the SNU. So SNU is x times sigmoid, which is, you can interpret as a continuous version of ReLU. Because ReLU have sharp edge near 0 and has 0 gradient when it's negative. Okay, so why don't you guys implement SNU? So other non-linearities. So this is activation class, and other non-linearities with sigmoid, 10H, ReLU. So torch.clamp will set any value of x equal to less than this value to 0, and let's implement SNU. And the gradient is already implemented, so don't worry about the gradients. You just need to implement the forward implementation of SNU. And the formula is here. It's x over 1 plus e to the negative x. All right, so it was easy, right? So you already have the implementation for sigmoid. So you just need to multiply, you just need to copy paste sigmoid, multiply by x, right? Okay, and once you have finished implementation, then let's plot the activation functions. So from a range of -5 to 5, let's do a subplot of the non-linearity functions and its derivatives. Okay, so like we saw in the lecture, ReLU, sigmoid, SNU looks close to ReLU, but it's continuous everywhere. And 10H, and if you look at 10H, the orange guy here, when both inputs are very large negative or positive value, the gradient is 0. Same thing for a sigmoid, and ReLU has a sharp step function like derivative here near 0, and SNU is continuous. Oops. Okay. So let's, for example, apply a linear map and SNU activation and look at the histogram again. Okay, just to give you some more time. If you're still here, just try to copy paste this so we can move on. You guys need more time? Okay. Okay, so here's the input and output. So we initialized the weight and scaled it so it's multiplied element-wise by square root of number of inputs, and we hit it with SNU, and that's the output. It works similar to ReLU in the sense that if you look at the activation function, negative values, it's going to be multiplied with something close to 0. But when it's not quite 0, it's going to have something that's non-negative. So we will allow some non-negative numbers after activation. Okay, so now it's time to stack multiple linear maps with nonlinear activation in between. So here we're gonna, upon given x, apply first linear, apply SNU, and apply second linear. So here, first in the MLP class, you need to declare the layer weights. So we have weight and bias for the first layer, weight and bias for the second layer, right? And this is the for call. I guess this is very straightforward. And given 2 by 64, and this is the hidden dimension. So after you receive this input, you're supposed to project the 64-dimensional vector to 256 intermediate dimension. And so here we already have specified the dimensions. So layer 1 is supposed to take the input and output a vector in hidden dimensions, which is of size 64. And linear 2 is going to take 64-dimensional vector and project it back into the original dimension. So temporarily, we blow up the representation space by a factor of how many? Factor of 4. Okay, so let's implement this. Once you're finished, run the last cell, so you get the expected output. So what is the expected output dimension of y? Right, 2 by 64. So one of the, I think I talked about this in the first lecture. So after PhD, I worked at a tech company, and I was supposed to do some task. And at Google, everything is a single repository, so you can look at other people's code and do things. And one of the surprising things was there was no manual or documentation. And there was so much code. And the advice I got was try not to read every single code, because there's too much, and there's no time to write any documentation because code is changing constantly, and a large portion of the code is machine generated, so it's hard to read. And the advice I got was just read enough so you can get your job done, and worry about not learning the entire code. Don't worry about learning the entire code, and just focus on accomplishing the task as soon as possible. And if you want to understand other people's code, look at other people's unit tests. So if you look at the test, it creates some input and checks if the output is as expected. So for example, input all zeros matrix, and you suppose your expected output 0, check that, and suppose you input all matrix of all ones, and expected output is number of dimensions or something like this. And it gives you an idea of what it does in terms of inputs and outputs. And same thing applies here. Don't try to learn everything about PyTorch. Just learn enough so you can get your job done. Okay, so let's look at the solution. So we're supposed to create 2 linear maps and activation functions. Dimensions are already given to you here, and we're going to use SNU. And for call, you receive input X. You apply W1, the first linear map, and apply SNU. And given the output of SNU, you apply the second linear map. That's output. Okay, let's see if the dimension is as expected. Yes, the input and output dimension is the same, and that's great. Okay, so let's open up the second notebook. Here we're going to do a backprop. Sometimes when you have too many sessions open, it's going to force you to close other sessions. Okay, so we have built a 2-layer MLP. Now it's time to apply gradient descent. So we already talked about competition graph, chain rule, gradient descent. And let's do a very basic exercise. We're going to do it in single dimension and extend it to multi-dimensions. So yeah, very basic gradient descent. So you have some differentiable function. To be technically correct, doesn't have to be strictly differentiable. It can, as long as it's sub-differentiable, it's okay. And what I mean by sub-differentiable, in coming lectures, we're going to cover subgradients. And if you take my graduate class, we're going to prove convergence of convex functions and sub-differentiable functions. But anyways, as long as it's sub-differentiable, it's okay. So hinge, value, all okay. So given some function f, which takes m-dimensional input, outputs a real number. This is going to be, in our case, most likely going to be the loss function, or a negative log likelihood. Then we're going to produce a sequence of iterates, these x's, so that as we continue, the function value decreases. Function value of xn is less than or equal to xn plus 1. And the running example we have is function here. It takes two inputs, x and y, and outputs a real number. Okay, so here is the function definition. So the detail is not very important. So it looks like this. So from the range of -4 to 4 in x and y, the more blue it is, the less the function output. So the optimal point is probably going to be somewhere here, right? Okay, so let's define the gradient. So input is x and y, output is two-dimensional, df dx and df dy. So let's implement the gradient function. And here, if you scroll bottom, we're going to do a random initialization of x and y and use a constant step size of eta equal to 0.0. And we're going to apply gradient descent 50 steps. And we're going to keep track of the trace, the current x and y's, so that we can plot the trajectory. And here, there's another to-do. Here, you're supposed to update the gradient of descent rule. And the rest of them is just for plotting, not important. Okay? So if you implement correctly, what's the expected output? So it's going to do a random initialization. So it's going to give you a trajectory. So let's say initial point is here. It's going to do some gradient descent and converge to here. If you log out, start here, it's not going to move. Okay? So you're supposed to implement the gradient function and the gradient update rule with a fixed step size. Once you're finished, run the cell and make sure you converge to here. Okay, let's look at the solution. Yeah, this is very basic stuff, right? So df dx, df dy, and gradient descent rule. You call your gradient function that you implemented and take your current x and y with step size eta, apply the gradient. Right? And let's give it a try. Okay, so this is what I got. You started off here through random initialization, and you ended here. Okay. Okay, so how about if you have composition of multiple functions? So here we talked about chain rule and computation graph and chaining different computation graph. And in computation graph, you started, you have, so computation graph by construction is directed acyclic graph. So there exists a topological ordering. So in forward computation, you start from left to right. And in backward view, you start from right to left. And when you compute your backpropagation, you first compute gradient of the loss with respect to itself, which is 1. So 1 is the base case. Start with 1. And for each computation node, you receive df dy, or dl dy, the upstream gradient. And given the upstream gradient, you're supposed to multiply the local gradient, which is dy dx. And by chain rule, you will be able to compute dl dx, which is going to be input to its predecessor compute node. We already learned this in computation graph lecture, right? Okay, so here, this is just, it just repeats what I've just said, just chain rule and composition of functions. And if you have chaining of these computation nodes and say x is z1, the output of alpha fi upon receiving zi is zi plus 1. So this is the cached for computation outputs. You need these to be cached so that you can use it during backward computation to compute the local gradients. And you just need to repeatedly apply the chain rule in reverse, and that's going to be dl dx, gradient of the final computation node with respect to the input. Okay, so here we have a linear function and quadratic function and polynomial function, and you're supposed to implement the gradients for all these guys separately. And then we're going to chain the three functions together. So f1 is linear, quadratic, polynomial. So this is going to define our forward view for computation. Linear, quadratic, polynomial is going to be chained on top of each other. This is for computation. And given the forward, this is going to be the visualization of how the function looks like. And we're going to try to compute the gradient of this guy, do a random init, apply gradient descent. So if you, for example, start here, where are you going to land? Right, you're going to land here. If you start here, you're going to land here. If you start here, you're going to land here. If you start here, you're going to land here. and that's what we're going to see. So if you have finished the forward computation, try to finish the backward as well. So here you need to cache the intermediate values during forward pass. Use that to compute the gradient. Okay, so first thing, for each function individually, compute the local gradient. That's the first thing to do. And then here, as you compute forward, cache the intermediate outputs of each computation node in ZS lists. Use that in your final gradient derivation. So all you need to do, so here base case is always 1, and given the upstream gradient, multiply the local gradient and repeat, and that's going to be the final gradient. And once you implement this, then we're going to apply gradient descent. And here, just write the gradient descent update rule, and we're going to visualize. So it's going to do a random init, I think. Gradient descent is called randomly initialized x, and let's see how this works. So you need to implement two things: local gradients for these individual functions, and cache the inputs in the forward, and compute the gradient with chain rule. That's it. And here, just 1 or 2 lines for gradient descent. Okay. Anyone finished? Okay, in the interest of time, let's see. Okay, so local gradients. For the linear function, derivative of this with respect to x is a. Quadratic function is 2ax plus b. Polynomial function it's basically the coefficient times x raised to I minus 1. And this test gradient function, what it does is it does numerical gradient checking. So sometimes if this fails, this is numerical gradient checking, so sometimes it can fail. If it fails, just run the cell again. So what it does is it computes the numerical gradient. So it computes f of x plus epsilon times ei. Ei is a standard basis vector minus f of x divided by epsilon. It does that for all dimensions independently, stacks it into a vector. That's going to be a numerical approximation of the gradient you have implemented. All right? Okay, so given the local gradients, we're going to chain the three functions on top of each other and draw a plot. This is how the function looks like, the chained function. And let's do for computation. So for each function in the chain, we're going to execute the function in order and cache the output to our list ZS, which stores the intermediate values of each computation node. For the gradient, you have access to ZS, and you're supposed to implement this, which is very simple. So here, this is the upstream gradient, and you have a list of functions which defines your computation graph, and in order, you're going to call the local gradients on each respective cache of the function output. So local gradient, upstream gradient times local gradient. That's going to be the upstream gradient for its predecessor node, and that's going to be the output gradient. Now it's time to apply gradient descent, and this f is the chained function. It gives you a list of intermediate values during 4 pass, and we have already implemented the gradient of this composite function, and we're going to do a gradient descent with eta. Okay, so that's the function and chained function forward and backward, and gradient descent. So it looks like it started here randomly. Gradient descent ended here. You can execute this cell multiple times, and you can also look at the output function value. So initially, the function value was 1.8, and it has decreased to 0.45, converged to local optimum. So execute the cell again for another random init. It started here and got stuck here. Again. Again. So here, the function value is 2.5. So this is somewhat a hack, but sometimes in optimization, one hacky strategy is do a random init, do that, say, I don't know, like 100 times, and you have rough sense of a judgment of whether your initialization is above average or below average. And once you have that statistic, then do multiple random inits and start when you're below average in the function value. Because sometimes you have to start here and do all the way down here, but sometimes you will initialize here or here, and you have a better shot of getting global optimum. Because if you initialize somewhere here, then it's impossible with standard gradient descent to ever land here. So you need to, in order to escape local optimum, sometimes you need to re-init. Okay, so we have extension to multi-dimensions, and we'll pick it up in the next lecture. Thank you.